So while I will have you calculate some test statistics and some p-values sort of by hand and work through these steps, I want you to know that R is available to help you, especially if you have large data sets. It will go through and do a lot of these calculations for you. So I think it's really important to note that. In this, the births data set for these North Carolina mothers is available in the open intro data set, so I just loaded it in. Okay, I can use the t.test function, and I'm going to say specifically to use the births data. And then here I'm going to use the column weight, and I want to see it broken down by, there's my little tilde, by smoking status. Okay, so this is going to do a difference of means t-test. And you'll see that it spits out, there's my test statistic. Maybe I should write this in here. This here, that's my test statistic. There's your degrees of freedom. Now this degrees of freedom is calculated using that really complicated formula. So if it doesn't match up, remember we used the minimum of the two, so we used the 49 degrees of freedom, right? So this would be what you'd get if you use the really complicated formula. So I just point that out. So if it's different than what you got before, that's why. And there's your p-value, right? So our p-value is slightly different than what we got before, and that could be for two reasons. We're using a slightly different, more precise degrees of freedom. We also ended up with a slightly different test statistic, and I'm confident that that comes from rounding error, right? So when I calculated my means and my standard deviations here, I rounded them all to 2 decimal places. And if you do it precisely, you're going to get a slightly different value. So I always recommend students use as much, to as many decimal places as possible, and carry those values throughout your calculations. So that might be why they're slightly different, but same ballpark, right? This t-statistic is very similar, and this p-value is very similar. One thing you will notice is that their test statistic is positive and ours is negative. So they must have set it up so that rather than group 1 being the smokers and group 2 being the non-smokers, they would have just flipped those. And that's totally okay. As long as you sort of start from the beginning, you specify what the first group is and the second group is. It doesn't matter which one you choose which to be which. One way you'll get a positive test statistic, the other way you'll get the negative test statistic, but the conclusions you make will be the same. And then also let's point out here, here's our confidence interval. So there's our 95% confidence interval there for the difference between the means. So this is as low as it could possibly be with 95% confidence, and this is as high as it could be with 95% confidence. Remember, we interpret that as 95% of the time we expect our confidence intervals to contain the true population means. So in this case, 0 is in there, right? So that sort of aligns with the fact that we did not reject the null hypothesis. So the t.test will certainly help you with these calculations, working out the confidence intervals and calculating the test statistics, but you'll still have to go through and do this last step, right? Where you make conclusions. You still have to be able to pick out the p-value, compare it to some alpha, and make some decisions and talk about it in the context. So it saves you a little bit of time, but it doesn't do all of the analysis for you. Again, maybe I should just say here, what conclusions would you make off the 95% confidence interval? Based on 0 being in that interval, I would say that 0 is a plausible value for the difference. So just looking at that, I can say that there's no evidence to suggest at the 95% confidence level that there is a difference between the birth weights of smokers, birth weights of the babies born to smokers versus non-smokers.